All right, so welcome to our department colloquium. So it's my great pleasure to introduce our speaker today, Professor Eva Andrei. Eva Andrei is a board of governors chaired professor in the Department of Physics and Astronomy at the Rutgers University. And she's a fellow of National Academy of Science, the American Academy of Arts and Science, the APS and American Association for Advanced of Science. And Andrei is also Moore Foundation EPIC Fellow, a recipient of French CCA Medal of Physics and the Lady Davis Fellowship and Rutgers Board of Trustee Award for research, the excellence in research. Andrei's current research focuses on the electronic properties of the two-dimensional materials probed by the scanning tunneling microscopy and spectroscopy and transport measurement. She's very well known for the 2010 discovery of Van Hove singularities in the twisted graphene, bilayer graphenes, and for the 2009 discovery of fractional quantum Hall effect in graphene. So I think with that, let's join me. Welcome to Professor Andrei to our department. Okay, so Eva, now floor is yours. Oh, by the way, before she starts, let me just to tell you that the way that we are taking a question, if there is urgent question, I'll read the Q&A and chat and stop her at appropriate place to ask a question. Otherwise, we will have a question and answer at the end after she finishes her talk. Okay, Eva.
Hey, thank you, Hey Yan, for this nice introduction. Over the last a little bit over a decade, since the isolation of atomically thin, one atom thick layers, the ability to probe them and to isolate them has completely changed the way we think about materials. So with these kinds of layers, it is possible to change the electronic properties and the properties of the material without changing their chemical composition. So one can use alternative means such as strain, the substrate overlaying one layer over the other, and to achieve something like a new material. So this is an exploding field of research. And what I can do today is only scratch the surface, just give you a little bit of an idea of what is so exciting about this and what are the sorts of things that we can do. And I'm going to talk about two examples, starting with superposing two graphene layers with a twist between the crystallographic axis. And that allowed us to achieve something that we call flat bands, and as I'm going to explain soon, the flat bands enable us to have strong interaction between the electrons and to induce various interesting new phases of matter, of electronic matter. The second part of the talk, if I get to it, depends on how many questions there will be, is creating the same kind of flat bands but with a totally different strategy, and that is by straining a material, by stretching it over kind of a bed of nails. You see it here. So these poke out of the material, and that induces something that looks like flat bands, but without breaking time reversal symmetry. We're going to get to that. So let's get started. So when you Google graphene online, you may run into this ad here, which I find quite fascinating, from Graphene Platform Corporation, who are trying to sell you graphene. And they put this material in the context of eras in human civilization, you're going from Stone Age to Steel Age to Silicon Age in the 50s, and now they are implying that we are in the carbon age. Because we have graphene, we have gone through all these ages, and we have, in a sense, revolutionized our civilization. Now, you may not blame them for this kind of claim. If you look at what's actually the kinds of things that have been seen in graphene, which is a one atom thick layer crystal of carbon, you might not blame them for putting graphene here, for putting carbon in this illustrious list of achievements. And over the 15 years since the discovery of graphene, it has amassed a huge number of superlatives. It's the strongest material ever measured. It's 200 times stronger than steel. It's the stiffest known material. It's the most stretchable. It can stretch by 25% without breaking. It's completely impermeable. So even though it's only one atom thick, no atoms go through it. No, not even helium atoms. So you can blow a graphene balloon and not have it sag on you within a day. Record thermal conductivity, and so on and so on. So this material has really taught us a lot of things, and in terms of uses, it has started to actually break into the market. So let's say this is from within the next 5 years, within the last 5 years, graphene has penetrated various markets. Of course, rackets, you might own a graphene racket, bicycle wheels, and that takes advantage of its remarkable mechanical strengths. Very, very sensitive sensors, sensitive to one molecule of gas. It has uses in energy storage, for example, much faster charging ability of batteries. In biomedical uses, a friend of mine has developed an artificial retina that was actually already implanted in blind people that is based on graphene. So there are many, many uses already that are coming on the market, and of course many future uses that people are dreaming about. But in spite of all these achievements, I would argue that it's not carbon, it's not its particular spot on the periodic table that is revolutionary, but what is the fact that it's really two-dimensional. So instead of carbon, I would put here two-dimensional materials age, because this is really what is revolutionary here. And since the discovery of graphene in 2004, there are many more one-atom thick materials that have been isolated and studied, and they have a huge range of electronic properties. Semiconductors, magnets, superconductors, topological insulators, and insulators, boron nitride, tungsten ditelluride, tungsten diselenide, and so on and so forth. And so by now, there's several dozens of these materials that have been isolated and that are being studied intensely. What's even more remarkable, that theorists were able to predict over 1,000 new kinds of two-dimensional materials that we haven't even started exploring yet, but they have predicted they can be isolated and used, explored, used for devices and so on. So the beauty of these materials is that you can actually stack them one on top of the other. And you can just pick and choose the properties that you like to create. You like to create a new material, so you can put the niobium diselenide, that's superconductor, put it on an insulator like boron nitride, putting on a semiconductor like molybdenum disulfide, and you can make a sandwich out of these atomically thin layers and achieve properties that you are looking for, engineer properties at will. Now you may ask, okay, why can't we just grow these with a molecular beam epitaxy? Why can't we grow this in the lab? It turns out that most of these materials will not grow spontaneously. When you grow crystals or when you make layers in your MBE machine, what grows there is what nature dictates is the most stable compound. And many of these layers that you can actually superpose, you can actually not achieve in any other way. Now, if you are a pre-millennial physicist, so if you studied physics in the last millennium, 1900s, what I'm telling you here might sound as a miracle, might sound as a surprise. You might not even believe it. Now, why is that? It turns out that it was already realized in the 60s that there is no long-range order in 2 dimensions. So when you go below 3 dimensions, because we live in a 3-dimensional world, if you try to make a 2-dimensional layer, it's very easy to create fluctuations out of the layers and the long wavelength fluctuations, and those are cheap energetically, and therefore they will be favored entropically. So they actually proved, and there are many works that follow them, that there is no long-range order in 2 dimensions. And if you don't read the small print, the conclusion is that you cannot have 2-dimensional magnets, you cannot have 2-dimensional superconductors, superfluids, and certainly no 2-dimensional crystals. So for a long time, actually for several decades, this concept has put a damper on research in 2 dimensions. And people who ventured into the field were always suffered pushback by colleagues who told them, oh, it's impossible to have a 2-dimensional crystal, for example. Now, here come Andrei and Kostya Novosellos, his students, and they decided, okay, we're not going to listen to these theorists. Let's see if we can cheat nature. And their idea was, okay, we have layered materials. We have materials like graphite. We have materials like molybdenum disulfide or boron nitride, and these materials have covalent bonds within a layer. These are very, very strong bonds. They're the strongest bonds in nature, but between the layer, the bonds are van der Waals, and they're very weak. And as a result, you can exfoliate them like mica or graphite. So you put a piece, you can just so the idea was, okay, let's do this conjurer's trick. You have a deck of cards. You can always pull out one card out of this deck. So this was the idea that they had. Let's create a 2-dimensional material and see what happens. And I'm going to show you a little video here, how this is done. And this is how it's done in my lab.
Take a Scotch tape and gently lay it down on a flat surface. Next, take clean metal tweezers and keep a thin graphite plate, and then place this gently onto the Scotch tape. Next, hold the Scotch tape at the edge of the graphite plate. Peel it off gently, and do this step several times until you obtain a nearly transparent region on the Scotch tape. After this, take a clean silicon wafer to transfer the Scotch tape graphene onto the wafer. Use plastic tweezers and gently rub the area of the Scotch tape where graphene may potentially be. Slowly peel off the Scotch tape so as not to break any potential graphene sheets. Use an optical microscope to view and find graphene. Graphene appears as a purple spots on the screen. At the center of the screen is multi-layer graphene, and at the right corner, lower right corner of the screen, is single-layer graphene.
Okay, so this is how we make it. Of course, making it this way is you get very small flakes. I mean, the record graphene flake that can be isolated this way is about 0.5 millimeter big. However, there are new techniques. There are techniques today to make huge swath of graphene that you can cover a whole wall. And these are the kinds of graphene that you're going to set that you can buy from these companies online. So next, I'm going to tell you about the electronic structure. And since I know that we have undergrads in this talk, I'm going to give you a quick recap of the standard model of condensed matter physics. So let's say we start from atoms. We have atomic levels here in this atom, and we start with a bunch of atoms, and we bring them all together to make what we call a Bravais lattice. A Bravais lattice is one where every atom has exactly the same neighborhood as every other atoms, and it can go out forever. Now, when you bring these atoms together, each atomic level breaks up into a band, creates a band that has as many, that contains as many levels in there as you have atoms in your lattice. The electronic wave function looks like this. It is almost a plane wave with a characteristic wave vector that determines the wavelength of the wave. The wavelength here, as long as it is larger than the interatomic spacing, these electrons can move almost freely within this lattice, and they can hop between the atom with this so-called hopping parameter T that determines how broad this band is. This is the bandwidth, it also determines the kinetic energy of the electrons. Now, the wavelength or the wave vector of these electrons live inside what we call the Brillouin zone. These are all the waves whose wave vector is smaller than the interatomic spacing. This is the Brillouin zone. This is what the Brillouin zone looks like for graphene. So now there's another energy scale in the system, and this is the energy cost to accidentally put two electrons on the same lattice point or on the same ion, and that of course costs Coulomb energy. So that gives you on-site repulsion. So now we have a competition between these two energy scales. So when the on-site repulsion is much smaller than the kinetic energy, we have a wide band. The interaction between electrons are very weak. They hardly see each other, and we get single electron physics. The energy is proportional to the square of the momentum, like for classical particle. The prefactor here we call m star. This is where we hide all our ignorance about what the lattice does to the electrons, and we call it an effective mass. So if the interactions are very weak, this m star is equal to the electronic mass, but of course this changes a lot when the interaction is strong. So now I can throw in a bunch of electrons. I can throw in my electrons, as many electrons as are allowed by these atoms, and the highest momentum is the Fermi. It's called the Fermi momentum. The highest energy that separates between empty states and full state is called the Fermi energy, and this is where all the action happens. Everything, all the states here that form what we call Fermi sea, and they are kind of inert. They're like a vacuum. Now, in the other limit, when the interaction energy is large compared to the kinetic energy of the bandwidth, we get what we call a flat band, and at this point, interaction between electrons become important because the kinetic energy is quenched. The electrons slow down and they can start seeing each other and interacting with each other, and that gives rise. That's where things get really interesting. That gives rise to correlated phases. such as superconductivity and so on. So what happens when U is large, you open a gap and the states that are occupied here can form interesting correlated phases. So this is what we are after. Condensed matter physicists we are trying to create the conditions that will give us these correlated phases. So let me go to graphene. When you have a simple metal with one atom per unit cell, for example, copper, you get this beautiful parabolic band structure, which I just showed you. The electrons in here behave as if they were free electrons. Now, if you have graphene, graphene is not a Bravais lattice, it is a honeycomb lattice. Now, why is it not a Bravais lattice? That is because you see this red atom here has a neighbor north, but no neighbor south. We call it A atom. And the blue atom here has a neighbor south, but no neighbor north. So we don't have this simple band structure. In fact, we have 2 atoms per unit cell. And normally this will give us an insulator. However, there is an accidental degeneracy. There is a destructive interference here that closes the gap, and the band structure looks like this very strange animal here. This was already realized way back in the 1947 by Russell Waals, who calculated this band structure. So notice that if it were not the pink region here is where the Fermi energy sits. So down here, all the levels are full, and up here they're empty. These are electron levels, these are hole levels. And if it were not for these points here, we would have an insulator. But these points are where the band structure closes, is where things get really interesting. So let's see what causes this strange band structure. In fact, there are only 4 ingredients that go into this band structure. So number 1 is the fact that we're 2-dimensional. This is critical. Number 2 is the fact that we have a honeycomb structure, which is not Bravais. Number 3 is that we have identical atoms. We have carbons. Both the red and blue sides are filled with carbon atoms. And lastly is that the hopping integral, the probability of hopping between the red and the blue side, is the same in all directions. So these ingredients here are what give us this strange band structure. One thing to point out here, if you look at the ingredients, none of them requires it to be carbon. In fact, if you put together these ingredients, you can create this strange band structure with almost anything. So people have done it with cold atoms. They've done it by taking carbon monoxide and arranging it in a honeycomb structure on top of copper with microwaves. So anything, they've also done it with atoms that are not carbon, atoms along the entire 4th column in the periodic table. So these conditions are purely geometrical. So let's zoom into this. The points here where the band structure closes, these are called Dirac points. And the band structure here consists of 2 cones, 2 what we call Dirac cones. In the red part here, we have electrons. In the blue part here, we have holes. And the Brillouin, the hexagonal Brillouin zone is here. K and K prime are inequivalent points in the Brillouin zone. And the energy momentum relations, unlike for the massive particles, free particles that I showed you before, is not quadratic in momentum, but it's linear in momentum. So this is in a sense exactly like photons, like the dispersion of photons or neutrinos. And as a result, we call these ultra-relativistic particles. The slope of the cones here is what we call the Fermi velocity, and it's purely determined by the lattice spacing A here and the hopping between adjacent atoms. So the Fermi velocity, which is equivalent to the speed of light if these were neutrinos or photons, is about 3,000 times smaller than the speed of light. Now, there's also degeneracy. So whereas with the simple band structure, the degeneracy was 2 because we could put 2 electrons in every state, spin up or spin down. Here we have an additional degeneracy, which comes from the fact that we have inequivalent cones here. Now, for the experts, the Hamiltonian, which basically describes the dynamics of these electrons, is called the Dirac-Weil Hamiltonian, and it looks like this. On top here, this is the K point, and on the bottom here is the K prime cone. Sigma here is the Pauli matrix. Usually it operates on spin, but here it operates on the sublattice degree of freedom. And P is the momentum relative to the K point. So this is a very simple Hamiltonian. And this K, and these are the 2 K cones. Now notice that they are related by time reversal symmetry. So if electrons in the K cone go clockwise, sigma dot P is basically the projection of this, what we call pseudospin on the momentum direction, the direction of propagation. So in this cone here, they're parallel to each other. In this cone here, they're anti-parallel to each other. So this gives them a helicity, because sigma dot P is basically what we call the helicity operator. So as a result of this linear dispersion, the density of state, which is the number of states per unit energy in graphene, is linear in energy and vanishes exactly at the Dirac point. Now, this is quite remarkable because it enables us experimentally to do the following experiment. So here, this is a typical device that we can make out of graphene. This is called, it's a field effect transistor. We take a piece of graphene and we deposit on a silicon dioxide on a silicon wafer, which is made out of n-doped silicon, which is a conductor, and it has a thin layer, 300 nanometer thick insulator, silicon dioxide, and then you slap 2 electrodes, source and a drain, and then you connect these electrons to the gate voltage. So what you to this metallic gate, to the silicon gate. So what you've created here is a capacitor. So when you change your gate voltage here, you can either put electrons into your graphene or pull them out. Now, how does this happen? So when I have a positive gate voltage, I'm moving my energy into the electron sector. A negative gate voltage moves my Fermi energy into the hole sector. Now, normally, if you have just a standard metal where the density of state is flat, it doesn't depend on energy. It's not so small. It's not zero basically at the band edge here. You cannot change the Fermi energy. You can't put enough voltage in this capacitor to change the Fermi energy. Or you change the total charge, but the Fermi energy stays stuck because it requires too many electrons to change it. Here in graphene, because of this linear dispersion, it takes 1 volt of gate voltage buys you about 7 times 10 to the 10th carriers per centimeter square, or it moves the Fermi energy by 80 millivolts, which is a huge amount. In terms of temperature energy scale, it's about 800 degrees Kelvin. Now, if you add a magnetic field out of plane magnetic field, what happens, you break up this band structure into what we call Landau levels, and the density of state now breaks up into these almost flat bands. And you can count them. The one that sits at the Dirac point is n equals 0. So if you go in the electron sector, they're positive. If you go in the hole sector, the Landau levels are negative here. And again, this is the Hamiltonian in zero field. When you apply a magnetic field, the magnetic field is basically the curl of a vector potential, and it comes into the Hamiltonian like this. So it gives you a shift in the momentum by this vector potential here, and it has the same sign in both K valley and K prime valley. So if you solve this, you see that the Landau level energy goes like square root of the applied magnetic field and the Landau level multiplied by the Landau level index, which runs over these integers. So you see the prefactor here is the Fermi velocity. So if you're able to measure this Landau level spectral, you can immediately extract the Fermi velocity of these electrons in graphene. So now this gives us some idea of how we can control the band structure in graphene. And the same can be done with other two-dimensional materials. So one way of doing that is just relax the condition that the three hopping parameters are the same. You can do that by applying strain, stretching the layer. Another way of doing it is to impose an external potential, like putting it on a substrate. So you can have a superstructure that flattens the bands. You can pluck out the individual atoms, and that gives you point defects, which have very interesting magnetic properties. You can apply electrostatic potential, and that changes the Fermi energy. You apply a magnetic field, and then you create flat bands. So these are a lot of strategies that you can use to change the band structure of this two-dimensional material. So as I said, what we are interested in is having flat bands, and then when you bring the Fermi energy into the flat band, what happens, you enhance correlation effect, and then all sorts of new and unusual electronic phases can arise, including ferromagnetism, Moiré insulator, charge density wave, fractional quantum Hall effect, and superconductivity. Now, the last item here, superconductivity, is probably the most exciting and what actually brought many of us into the field. And back already in the 90s, this idea started in a Finnish group. And here there's a paper from 2007 by Volovic that argued that if you have a flat band, and you bring your Fermi energy into the flat band, as an example, he brought graphite, you can achieve room temperature superconductivity. So that was a huge incentive for people to start looking for flat bands and to start trying to manipulate the Fermi energy there. Of course, you cannot do that in a bulk material because you can't change the Fermi energy. So in a bulk material, you just get what you can get. But in two-dimensional materials, you can actually manipulate both the band structure and the position of the Fermi energy. So for example, so we have, now, of course, Landau levels, when you put apply a magnetic field to either graphene or any other two-dimensional material, you create Landau levels. And these are the quintessential flat bands. So you might say, okay, we already have flat bands. Why bother to look for other ways of making flat bands? Now, now here, we must apply a magnetic field in order to create these flat bands, these Landau levels. And by bringing the Fermi energy into these Landau levels, indeed, you create the strongly correlated states, in particular fractional quantum Hall effect, and this is from our 2009 paper, that you create a plateau here at one-third of filling, which means that for every electron, you have 3 flux line lattices that penetrate your sample. So this creates a sort of a composite particle that where you have every electron grabs 3 magnetic flux line and moves around with it, and that gives you what we call a quantum Hall plateau here that is seen in the Hall conductivity. And that is a signature of having created this new and correlated phase, which is very interesting in itself. However, the fact that we require magnetic field to create these flat bands is problematic because magnetic field and superconductivity don't like to, are inimical to each other. So this doesn't help us much. If we want to achieve a room temperature superconductor or any kind of other phase, we would like to be able to create flat bands without breaking time reversal symmetry, which a magnetic field does. So can we do that? How can we create flat bands without breaking time reversal symmetry? So there are several strategies. So the strategy are based, we can either create it by strain, which creates which creates pseudomagnetic fields. We can create it by fine-tuning competing hopping parameters. For example, nearest neighbor hopping and next nearest neighbor hopping gives you a geometrically induced flat band. We can do it, and this is what I'm going to talk about, by superposing two graphene layers and creating a Moiré lattice. And here you have a competition between hopping within the layer and between layers, inter and intra-layer hopping. And when the two are roughly comparable to each other, you get a almost perfectly flat band. The other strategy is to apply strain, and it turns out the strain looks exactly like a vector potential, which gives you something that looks exactly like a magnetic field, except that it has opposite signs in the two valleys. So that gives us a strain-induced gauge field, which gives you pseudo-Landau levels, flat bands, without breaking time reversal symmetry. If I have time, I'm going to tell you about this as well. And the third way of doing it is line graph lattices, that are naturally have geometrically induced flat bands. These are the Kagome, the dice lattice, the lib lattice, and there are many more. And then you get a destructive interference between wave function tunneling, between nearest neighbors, between corner and lines here. So then you get flat bands that coexist with non-flat bands, with Dirac cones, essentially. So I'm going to focus initially on just the twisted bilayer graphene. This is called magic. This is at magic angle Moiré lattice. Okay, so let's start with twisted bilayer graphene. So first, I'm going to just tell you a little bit about the experimental technique. How do we detect what's going on? How do we see the band structure, and how do we see the lattice itself? And this is done with scanning tunneling microscopy. You bring a sharp tip to your metal, you apply a bias voltage, and you measure the current. And when the tip is close enough, you get a tunneling current here, which depends on two parameters. One is it depends exponentially on the distance between the tip and your substrate. And by rastering the sample, forcing the current to be constant and keeping the bias constant, and having a motor that the feedback motor, you can actually create an image of the atoms that you have in your lattice. In this particular example, this is the graphene lattice that we actually measured in our lab, and every corner here is a carbon atom. Another thing that you can measure with scanning tunneling microscopy is actually spectroscopy. You can extract the density of state here by taking the derivative of the current with respect to the bias, and that gives you direct access to the density of state. And then you vary the energy. You can measure the density of state as a function of energy. So this is what it looks like for graphene, exactly as predicted theoretically. You have a linear density of state here, which vanishes at the Dirac point here in green. And the Fermi energy in scanning tunneling microscopy is the zero of energy. So you can actually, by gating your sample, you can separate the Fermi energy physics from the Dirac point physics. And of course, then you can apply a magnetic field, and here pop out the Landau levels. And by fitting the energy of these levels as a function of their level index, 0, 1, 2, 3, 4, or as a function of magnetic field, you can extract the local Fermi velocity. So there is a lot of things that we can do just with scanning, tunneling, microscopy, and spectroscopy. So here is our measurements on twisted bilayer graphene. This was done back in almost a decade ago. This is a TM, transmission electron microscope grid. This is not graphene, where graphene was deposited on it. This was graphene grown by chemical vapor deposition. And when you zoom into one of these holes, so these are holes in the grid, graphene was deposited on top of it. Here, graphene is suspended, and because it's one atom thick, it's very sensitive to the substrate disturbances. So you really want to suspend it, and in this case, you get a clean surface, a clean response, without having to worry about all sorts of randomness that's introduced by a substrate. And here, zooming in, this is our gold grid. Here we have a single layer graphene, twisted layer graphene. And what is interesting here is that there are many different twist angles that you can find in a layer like this, in a sample like this. This was totally serendipitous. We intended to study a single layer, but in fact, what we had here is many twisted bilayer graphene, and it turns out that we made lemonade out of a lemon here. It turns out that we got very interesting results. So let me show you what happens when you superpose two layers. Here we have the first layer of graphene. I'm going to bring another one on top and twist it. So what happens, you create this super pattern here, which we call a Moiré pattern. And the smaller the twist angle is, the larger the period, the super period of the pattern. You see the pattern period is inversely proportional to the twist angle here. So what we have here, what are these bright and dark spots? The bright spot corresponds to the top layer being, the atoms in the top layer being precisely aligned with the atom in the bottom, so that they completely eclipse the bottom ones. Whereas the darker region correspond to an A atom in the top layer sitting on top of a B atom in the bottom layer, and the B atom in the top layer having no neighbor underneath. So this gives you these darker regions, which are actually triangular. Here, these are the atoms that have neighbors underneath, and we have two kinds of such neighborhoods. One where the B atom on the top layer is on top of A atom in the bottom layer. So this is what this pattern is doing here. But this is not just a pretty pattern. It turns out that energetically, it's much more costly to have an AA region than to have this AB or BA region, which are called Bernal stacking. So if it can, the system will prefer not to have AA regions at all, but of course, this is not possible. So when the angle is very small, the system, the lattice is distorted in such a way as to completely squeeze out, almost completely squeeze out the AA region, and it's mostly AB or BA. And this is a saddle point in between. So the AA regions, because they're energetically unfavorable, they actually stick out of the plane. And this is what we see in scanning tunneling microscopy. The density of state also actually has peaks in the AA region. So here's what we saw. So here we have graphene layer with a twist angle of 20 degrees. the density of state looks more or less like a free, a single layer graphene. It's kind of V-shaped with a minimum at the Dirac point. The angle, of course, we know the angle by measuring this period here. We can also measure it from the Fourier transform of the period. Now we go to a smaller angle. This one is now 3.5 degree. Now you see these peaks started appearing. Density of state now is no longer completely different from that of single layer graphene. And then we keep decreasing the angle. Now at 1.8 degrees, these peaks have moved in even more. They've come closer together. And look, they become sharper as we move in. And here we've reached what we call the magic angle, 1.1 degrees. And the two peaks have merged into one. This is a flat band that it has a high density of state and it's quite narrow in energy. The Fermi energy is sitting within this flat band and we see a small gap opening. So that is suggestive of a correlated state. And then as we continue to decrease the angle, now this is 0.28 degrees, now you see these AA regions, which are the bright region, have shrunk as much as they can. They're down to about less than 10% in the area of the Moiré unit cell because of this energetics. There's a lot of strain built into this. Of course, you can't get rid of the AA just because of topology. So these are kind of like vortices, and these are connected by lines, which are these saddle points. That a lot of interesting things happening there, but I will not discuss it here. So, so here we plot the distance between those peaks, which we call Van Hove singularities, as a function of twist angle, and we see that at about 1 degree, it closes down. And that's what we call magic angle. This was called actually after our paper. And then we can also measure the Fermi velocity, the velocities of the electrons as a function of twist angle by using Landau level spectroscopy. And here we have a few points. And then we just also the red line is the theoretical calculation. And you see that at about 1 degree, the Fermi velocity vanishes, which means the electrons slow down so much that they can now interact with each other. And this is where you expect to have a correlated state if you bring the Fermi energy within that flat band. So this is 1.1 degree, that's where you create, it looks like you create a flat band. So what's going on and why do we create a flat band? So here we have a red graphene layer on top of a green graphene layer. We see the Moiré pattern that is formed. In the reciprocal space, you see the cones from the bottom layer, the Dirac cones, how they, and I've plotted them all, although only 2 of them are inequivalent. So you see that they merge at some finite energy here. That's in the Brill, you can also plot the 2 Brillouin zone from the top layer and the bottom layer, and they create a mini Brillouin zone here, which is a mini Brillouin zone of the whole system. That is, of course, much smaller. We've broken down the band structure into small regions, and now we have 8 orbitals per Moiré cell. We have 2 for valley, 2 for sublattice, and 2 for spin. So in order to fill a band, you need 8 electrons to go into each Moiré cell. So the filling, we're going to call it, let's call the number of electrons that the filling of the band is n over n naught, where n naught is 1 carrier per Moiré cell, and n runs from -4 to +4. -4, so you have -4 for the whole sector and +0 to +4 for the electron sector. So when you throw 1 electron into the whole band, the filling is -3. When you throw 1 electron into the electron band, the filling is +1. So now if we look at these 2 cones these 2 cones, let's say that that belong to the K values of the top layer and the bottom layer, you see that there's an energy at which they cross each other. The distance between the cones here in K space is just proportional to the twist angle. So this is our Hamiltonian, the Hamiltonian for in the K value. This is just in this Brillouin zone for the top layer and the bottom layer. If they don't interact, if they don't hybridize, they're completely independent of each other and they just go through each other. However, if we allow tunneling between the layers, which happens when they're very close, you get hybridization, and at the point of the intersection, you create a saddle point in the band structure, which gives rise to these Van Hove singularities, which we have seen in the experiment. So a saddle point in the band structure translates into a divergence in the density of state, or a large peak in the density of state, and this is what we call Van Hove singularities. Now, the distance between these Van Hove singularities was the original distance between the intersection of the cones minus the energy. This is not a distance, the energy difference, minus the energy, the hybridization energy. So okay, so this is a simulation of the band structure as a function of twist angle. You see, as the twist angle decreases, you break the band structure into smaller pieces, and when you get to the magic angle 1.1, you have a flat band. So this is exactly what we are seeing here. And as you keep decreasing the twist angle, the band becomes broader again. Okay. So fast forward to 2016, when a group led by Emmanuel Tutuk invented a technique to actually control the twist angle between layer. And this is done, this is illustrated how this works. You basically use the different stickiness of different materials at different temperatures. So you put down a graphene layer, you take bore nitride, which is a sister material, and you heat it up. These are some polymers. You press it down, which now the graphene layer sticks to the bore nitride, lift it up, you've torn it in two pieces, and now you take the bottom piece, it's sitting on a goniometer, you rotate it, but whatever twist angle you want, and we have huge control over that, and then you stick them back together, and that's how you create a twisted graphene layer with a pre-designed twist angle. And so this is what people started doing, and this is the group of in the MIT group of Pablo Jarillo Herrero. They made a field effect transistor out of graphene. So you have a twisted bilayer graphene here that is protected from top and bottom by bore nitride. It's protected from random potentials that comes from various that would come from various substrate, and then they cooled it down close to absolute zero. This is in a dilution refrigerator, and measure the transport properties as a function of filling, and the vertical axis here is temperature, and the color code is for resistance, and they saw that at a filling of -2, which is about when you have 2 electrons in the whole band or 2 holes in the whole band, you get an insulator. But as you move off that filling just a little bit to either right or the left, the material becomes superconducting. And this was absolutely a huge surprise and excitement. It was announced at the 2018 March meeting in LA, and it was like the almost as exciting as the discovery of high temperature superconductors in 1987. So people got very excited about this. But now if you look at this, the critical temperature of this superconducting dome is pathetic. It's like less than a degree. It's 300 millikelvin. Why should anybody care about such small superconducting temperatures? I mean, we have much higher, up to 200 Kelvin. So what's the big deal? So the big deal of this, the big deal was the fact that the similarity to high temperature superconductors. We have an insulating phase flanked by two superconducting domes. Just like in the cuprate superconductors, there is strong coupling between them. So people were hoping that by looking at graphene, which is a much simpler material, they will able to figure out what's going on with high temperature superconductors. And one other reason for the excitement is in the phase diagram of high temperature superconductor, every point here is essentially a different sample. It has to be synthesized, and it takes months and months to generate the phase diagram of high temperature superconductors. Whereas this phase diagram here can be obtained very quickly because all you need to do is change the gate voltage in your sample. So people got very excited about, and then they started asking question, is there a pseudo-gap phase, which we see in high temperature superconductors above the superconducting dome? Is there nematic order? Is this a strange metal, which basically means that the resistance is linear in temperature down to the lowest temperatures? And so all these questions all of a sudden popped up, and people started trying to answer them. As we did, so we said, okay, let's see. So our question is it? We could not go to the very low temperature with STM to see the superconducting gap, but we could be a little bit above the superconducting gap and ask questions about the nematic phase, the pseudo-gap phase. So we prepared a sample the same with the tear and stack technique, put it in our STM, protected from the bottom with boron nitride, and looked at it. So, and this was a sample that was 1 degree. This is magic angle. And you see this beautiful Moiré pattern here. These are the AA regions surrounded by the AB regions. And zooming in, you can see the atoms. You can see that they're right on top of each other in the AA regions and form AB stacking in the AB regions, or Bernoulli stacking. The next thing that we did is look at the density of state, which is the DI/dV map. And since we now could move the Fermi energy because we have a gate voltage here, we first moved the Fermi energy way below this flat band. One of the advantages of STM, scanning tunneling microscopy and spectroscopy, is that you're not limited to the Fermi energy. Whereas with transport and ARPIS, with most other techniques, you can only look at what's going on at the Fermi energy, or in ARPIS only below the Fermi energy. We can actually scan the whole energy range. So as a result, we park our Fermi energy way below the flat band, and this is what it looks. We see the flat band appearing here. The width is about 40 millivolts. Then we park the Fermi energy way above the flat band. So we fill the band. Again, it looks the same. And now we can walk with our Fermi energy and put it inside the band to see whether we get a correlated state and what it would look like. And sure enough, when we bring the Fermi energy within this flat band, we open a gap. Actually, this is a pseudo gap. The gap doesn't go to zero. The density of state doesn't go to zero at the Fermi energy. So we see that we have induced a correlated state. We have induced that gap, and we can now look what's the nature of this gap. So,
Eva, can you wrap it up?
I think I'm running out of time, so let me just wrap it up here. Okay, so what we have seen, with the scanning tunneling microscopy, we're able to actually, this is the topography, we're able to measure the charge, the local charge, and we've seen that when the Fermi energy is within the flat band, we get this nematic order. Just like in high temperature superconductor, there is nematicity in the pseudogap phase. Here we have a pseudogap, and the charge we have in the red regions, we have 1 electron per Moiré, whereas blue region, we have 1 hole per Moiré. So we have alternating stripes of positive and negative charge. And this is spontaneous. And it only happens when the Fermi energy is within this flat band. When we are outside of the flat band, it doesn't happen. So let me summarize here. What we have seen is that when you bring the Fermi energy within the flat band, you get a pseudogap phase. This is called the pseudogap. This is very similar to what is seen in the high temperature superconductors. And we get a nematic charge phase of charge stripes, which is very much like what one sees in the high temperature superconductors. Strange metal behavior has been seen in our transport measurement, and as well as in other groups' transport measurements. So it looks like that we can actually check all these questions here. Does it actually teach us something about high temperature superconductors? Not yet, and maybe not at all. In fact, the system is quite different from the high temperature superconductors we now know. So just phenomenologically, it's different. For example, whereas in the high temperature superconductors, there are only 2 superconducting domes. Here we have many domes. We have domes whenever we go between integer fillings. Whereas in high temperature superconductor, the insulating and superconducting phases are cooperating with each other. They are closely related. It turns out that in magic angle twisted graphene, they are competing with each other. So when we suppress the insulating behavior by screening the Coulomb interaction, the superconductivity is enhanced. Very different from high temperature superconductors. And we have, when we put 3 electrons per Moiré, we get orbital ferromagnetism. We have a slew of topological properties, churn insulating phases at integer band fillings. And you can see some of these references here. Some are ours that discuss these different aspects and how the physics of magic angle twisted bilayer graphene is different from that of high temperature superconductors. Whether it's going to teach us something about high temperature superconductivity, the jury is still out. And let me go to the summary. So I haven't had time to tell you about strain. So this is a summary. When we superpose 2 graphene layers, actually any kind of crystal, you create a Moiré pattern. This is a super lattice here. That in the density of state, you create Van Hove singularities that merge at a magic angle, which depends on the ratio between the Fermi velocity and the hopping. This magic angle happens at about 1 degree, and that gives you rise to a flat band. There are superconducting domes flanking an insulating phase, and actually flanking insulating phasing at almost all integer fillings, or Moiré fillings. And at higher temperature, we see in scanning tunneling microscopy a precursor to superconductivity, which is a pseudogap phase and nematic order. And this is the team. The pictures here are the people who did the experiments in our lab. We have our Japanese collaborators who sent us the boron nitride, and we have Andrei group who sent us the buccal graphene, the on-ion diselenide, which I didn't have time to discuss, and the theorists who help us analyze the data. And of course, this kind of work raises more questions than it solves. And there are many, many open questions and many challenges, both theoretically and experimentally, that are left. So among the open questions are, what is the pairing mechanism of the superconductivity? What are the broken symmetries? What is the nature of those various insulating states? And we know that now that these are topological states. Can it actually help us? Can we get high temperature superconductivity in twisted bilayer graphene? What is the highest TC that we can achieve? So far, the highest TC is about 3.5 degrees Kelvin, which is very small, which is kind of doesn't make any dent in superconducting technology. And there are many experimental challenges left. And thank you for your attention.
Thank you. That was a really, really interesting talk.